All right, so let's go ahead and get started. So welcome back, everybody. I hope you had a nice New Year's and hope your New Year's going well thus far. For our first speaker for the new year, we have Lucas Kocia. Lucas is a member of Sandia's Sandia National Laboratories Quantum Algorithms and Applications Collaboratory in Livermore, California. He's worked on quantum adiabatic algorithms, classical algorithms for quantum simulation, and also quantum contextuality and semi-classics. Today, he is going to talk to us about digital adiabatic state preparation errors scale better than you might expect. Thank you for joining us today, Lucas. Please feel free to take it away.
Great, thank you, Gregory. I'm going to just share my screen again. And thanks for bearing with me with scheduling issues. I was supposed to go in December for the others who don't know, and jury duty beckoned, but ended up not beckoning. So I'm going to be talking about. So I've never attended this seminar, so I don't know the formality of it. If you interrupt with questions, usually please do so. I'm okay with that, and I'll try to talk for I don't know, 45 to 50 minutes. The title is Digitized Adiabatic State Preparation Error Scales Better Than You Might Expect. We just heard from some referees that we might want to change the title so that it ages better, since expectations change. But this is what we have so far, and that's my name. So the paper is on the archive right now, and I'd like to acknowledge my colleagues and co-authors, and I'd also like to quickly acknowledge some sources of funding here at Sandia that I enjoy, specifically OverQC, AQC, which are listed here. And please feel free to look up the paper if you'd like to follow along. So the sort of overarching subject that I'm going to be talking about is quantum state preparation. And it's an important task in a lot of quantum algorithms, specifically in quantum simulation. Usually you want to evolve from some structured initial state, frequently one that's easy to prepare for you on your quantum device, to some final state, which has a well-defined overlap with what I'll eventually define as ground states, and then you want to do phase estimation or some non-trivial task using your quantum device on this final state that you've prepared. And this is important for a lot of different quantum algorithms. Applications range widely. Field theory, electronic, like chemical electronic structure tasks are some popular ones. It's also important in the sort of the nascent field that some of my colleagues are working in quantum sensing. Highly entangled many body states are particularly sensitive quantum sensing candidates, and you have to be able to prepare such highly entangled states, which is a non-trivial task. One generic approach to quantum state preparation is using the adiabatic evolution protocol, wherein you have a time-varying Hamiltonian H, which is parameterized by some control curve U. And generally, U will be time-dependent. And H, when U is equal to 0, is equal to H1, which corresponds to a Hamiltonian with a ground state that is quote unquote easy to prepare on your quantum device. And when U of t goes to 1, H corresponds to H2, which is the Hamiltonian that has the ground state that you want to prepare. So the ground state corresponds to the state you're interested in doing actual calculations on using a quantum algorithm. Generally U of t can, in the simplest case, be simply proportional to a linear ramp or rather can be just a linear ramp, but you can generically use any sort of function that's bounded between 0 and 1 you'd like. Of course, to prevent or minimize diabatic leakage, you generally want to choose a profile for your control curve that is flatter during avoided crossings. Unfortunate, well, a lot of quantum devices that are available right now and that are being developed are not analog quantum devices, which is to say that they have decompositions into quantum unitary gates, which you can think of as a discretization of an analog quantum architecture. And so to run on these sort of universal quantum, what will hopefully be eventually universal quantum computers, you need to, what a lot of individuals call digitize. You need to digitize or discretize your adiabatic evolution. And so a very sort of a priori simple way to do this is through Trotterization. And that's where you take your continuous time parametrized unitary, given here in this first line in the center, which is a time-ordered exponential with where the exponential argument is integrated from 0 to some final time capital T, and you chop it up into what I've indicated here as R steps. And the way you chop it up is you basically let H take the value at the particular time that you're chopping it, and you just make it a delta T time step. Here in the second line, I've given a first order Trotterization decomposition into R time steps with time step delta T. And in first order Trotterization, you have two alternating terms, which are called U1 and U2 here, where U1 just corresponds to the delta T time step with H1 having the weight or coefficient that it has at that K times delta T time step. And U2 correspondingly corresponds to has the weight of H2 only. This is sort of the simplest Trotterization scheme. It's a first order Trotterization scheme, and I'll quickly define what that means in a second. But first, let me just take a quick tangent to talk about the parameters. I'll be kind of flipping through just talk because sometimes it gets confusing. There are three parameters that I've already defined here. Delta T, which is the time step R, the number of time steps I've discretized my evolution to, and capital T, which is the total time. There are only two of these are technically dependent. You can always write the third one in terms of the other two. And so in general, I will be fixing one of these. And so you'll only have one free variable at that point. So just to set the stage for that. So I mentioned this is a first order Trotterization. Why is it first order? Well, the operator norm error between U of T, which is the continuous non-Trotterized unitary, and the first order Trotterized unitary into delta T time steps scales asymptotically as T times delta T times, with some coefficient, which I'll actually begin to neglect as I move forward, and just refer to this as order delta T scaling. So that means that as the unitary that you're Trotterizing, as its total time increases, your first order Trotter error will linearly increase as well if you fix your time step. And similarly, if you fix your total time and starts decreasing your total time step, your Trotter error will be bounded by a corresponding linear decrease in Trotter error. So that's why it's called first order, because the It's called first order because the exponent on delta t here is 1, and you can go to higher order ones and make that scaling better. Any questions at this point? Okay. So conventional. So here we're going to be considering trotterization of adiabatic or near adiabatic control curves, and you can import your conventional wisdom on error scaling that you have from just first order trotterizing diabatic dynamics. And what that means is if you ask what is the state prep error, so state prep error I'm going to define as more formally in the next slide, but for the sake of heuristics here, it's going to be diabatic error plus Trotter error. And a general, how do we expect this to scale? Well, diabatic error, you can actually bound pretty loosely by generically, as long as there's a gap, with an asymptotic scaling of inverse quadratic in total time for constant if you fix the time step. So that means, generically speaking, regardless of your control curve, as you stretch out your control curve to a longer time t, you expect your state prep error to decrease quadratically with the amount you stretch that total time. On the other hand, we just showed and motivated that first order Trotter error, operator norm error, scales linearly with total time. And so as t gets large, you expect, obviously, that scaling to dominate over the diabatic error scaling. And so heuristically, your conventional wisdom is that trotterizing adiabatic control curves should actually be dominated by Trotter error that linearly increases with the total time of the adiabatic evolution of trotterizing, which is unfortunate. So another way to put this is adiabatic evolution. If you take any sort of time slice of it, interval of time, it'll look more or less constant, which is what I have on the left there, a graph of u versus total time t. Adiabatic is slow, so if you take any sort of, if you look at any local part of it, you expect to be more or less constant. As you increase the total time of that slice, you expect from your conventional wisdom that in order to maintain the same amount of error, you need to decrease your time step proportionally. So if you increase your total time by a factor of m, you need to decrease your time step by a factor of m. And so that means that as t increases, you actually need the number of your time steps to increase quadratically. Okay, so let's see if our conventional wisdom is reflected by reality. And as a first step, we will define what we mean by our error metric, which I sort of heuristically defined as diabatic error plus Trotter error on that earlier slide. So we're going to define what I'm going to call infidelity as 1 minus the absolute value of the inner product between our initial state evolved perfectly. And by that, I mean a continuous time evolution done to infinite time. So it's definitely adiabatic. And so it's the inner product of that with the same control curve, but shrunk to potentially finite total time t, and then subsequently trotterized into delta t time steps. So hopefully this definition makes sense in that it captures both diabatic error, because t, capital T, can be finite, as well as Trotter error because delta t can be non-zero. I want to point out that I'm going to call this infidelity, but a lot of people in the community actually call infidelity something like 1 minus the inner product squared. So just keep that in mind if you're trying to compare to other results. It turns out that not squaring it is a little mathematically easier because as it turns out, this is shown clear from the second line actually, I of t defined this way serves as a lower, or is infidelity defined this way is upper bounded by operator norm error. And so that means that we can immediately bound this definition of infidelity by our first order Trotter naive scaling of delta t times t. So as a first example, I'm going to consider H1, just a two-level system, one qubit, where our initial Hamiltonian is just the X Hamiltonian, and we start in the plus state, ground state, and our final Hamiltonian is the Z, so we are trying to target ending up in the zero state. And my control curve here is just a linear ramp, so it's T over capital T. And you'll see right away that the scaling does not accord with our conventional wisdom. So it doesn't scale. So here, again, I fixed delta T just like I had here. This is the exact same graph. But instead of increasing with capital T, it decreases. In fact, it decreases as capital T squared. So it's 1 over T squared. Now, keep in mind, so I should point out that this holds as long as delta T, the constant that I've fixed here, and I'm showing 3 values here, is below a particular threshold value. So in particular, for delta T's above 1, which is above 10 to the power 0, you don't get the scaling. And just as a foreshadowing, that delta T value threshold is on the order of the norm of H1 and H2. But if you're below that value, if your constant delta T is below the value, you get the scaling, which doesn't accord with our conventional wisdom. And so let's take a closer look. So here, instead of fixing the time step, I've fixed the total time, T. And I'm varying the time step on the x-axis. So log plot. Now, when delta T is very large, keep in mind, I'm actually varying, delta T gets larger as you go from right to left, not from left to right. As delta T gets larger, so you're on the left-hand side of the paper, what you expect is there will be a point at which the Trotter expansion is non-convergent because of my foreshadowed threshold that, you only get a convergent Trotter Trotter expansion if your time step is below some threshold corresponding to basically proportional to the norm of your alternating H1 and H2 terms. So there you see that our infidelity basically skyrockets to 1, which is its maximum value. On the right-hand side, on the other hand, your time step is becoming infinitesimally small. And so it's basically your evolution, your Trotterization in that regime is approaching the continuous unitary for that fixed total time T. And so you can see there that your infidelity plateaus at something like 10⁻⁶ or something, which you can calculate is what you expect from your diabatic error. So it's a finite time T, so you expect still for there to be some diabatic error, so we get that. And so those 2 regimes are well understood. What is strange and doesn't accord with our sort of traditional heuristic from this view, where a fixed total time T is the middle of this graph, because here we expect delta T scaling. What you can actually find is that the middle regime is bounded by delta T squared, and more importantly, the amplitude is also bounded by 1 over T squared. So we expect to find in this wide regime, order T delta T and or not. So this is sort of a different way of looking at it than the prior graph, by fixing a different set of parameters. So clearly, the error bounds that we had before, where we set I of t, our infidelity, to be upper bounded by delta t times capital T, is very loose. And so can we tighten it? And this was a very appealing question for us because apparently different groups have observed scaling like this in different settings in the community, but not too much has been published about it. And then I'll be commenting at the end. One sort of sub-community that has seen this is the QAOA or QAOA community. And so we were really interested to formalize what exactly was going on here. Even though this is somewhat surprising, perhaps, it's also from another perspective, not surprising and might be expected, because this error scaling for the infidelity is based on just naively applying the triangle inequality to the first order Trotter bound. So the first order Trotter bound is really only for one time step. You can apply it to R time steps just by applying the triangle inequality. That's what gives you the delta t times capital T scaling. But obviously the triangle inequality does not take into account coherent effects or any particular structure. And we have some glaring structure here, namely that we're trotterizing an adiabatic evolution. So you expect there to be something else that trotterization error can perhaps benefit from. Any questions so far? Okay. So here's our main contribution, which is we derive much tighter error bounds that well, maybe that's a little bullish, that explain some of the observed behavior. Okay, so I'm going to present the two theorems sort of back to back and give you a heuristic explanation for their proofs. So the first one is more of a general theorem, and as a result, I think it's somewhat less interesting, but also maybe more interesting for other people. So given an adiabatic evolution where you have a Hamiltonian parametrized by a control curve U of t, where you have two terms, H0 and H1. I don't know whether H0 and H1 now. They used to be H1 and H2. If you first order trotterize that, generically, you're going to be bound, your infidelity is going to be bounded by the minimum of 1, because that's the maximum error you can get. Something that'll scale as the Trotter, as a standard first order Trotter bound of order T delta T. And a third term, which is a tightening of the bound, which is order delta T plus order T delta T squared. This is a shortcut way of writing the result. It's sort of an informal statement of the theorem. The linear combination of two terms, like order delta T plus order T delta T squared, doesn't make sense if you put order parameters on either side, on each one. The coefficients are actually derived in the paper, but it's hard to fit everything on one line. So this is what I ended up doing. Anyway, so you have that term, which is a tightening of the bound. And then all of that, which really is all, that first min term comes from Trotter error. You have to add the diabatic error, which is that final term. So let's quickly focus on that tightening of the bound term. You have, how is it a tightening? Well, the first one, order delta T, does not depend on total time. So that means that as you increase your the length of time of your adiabatic trotterization, if you're dominated by that term, you expect there to be no change in your Trotter error if you fix time step. The second term, order T delta T squared, is a second order Trotter error scaling. So what this means is that you expect sort of second order Trotter error scaling instead of the first order Trotter scaling in certain regimes. And as I write here on my note, point 3, this improved scaling is very similar, and we make that explicit in the paper, to recent tighter bounds for the trotterization of time-independent evolution. That was shown by Layden et al., I believe at IBM. And so the source of this tightening of bound term actually comes from coherence effects, coherence between the endpoints and the center and the middle of evolution in any time independent evolution, which you can sort of heuristically imagine any time slice, any time slice of adiabatic evolution is very similar to, since it's so slowly changing. Theorem 2 is the one I'm going to be focusing more on. And what we show in theorem 2 is if you add additional constraints, so you have an adiabatic evolution with a Hamiltonian between H0 and H1, and you go completely from H0 to H1, or more formally, U of 0 is 0 and U of t goes to 1. And on top of that, you add this constraint that U of t is infinitely differentiable. Then you can show that that bound tightens a lot more. Your infidelity is now bounded by the minimum of 1 and order delta t squared over capital T squared, plus the diabatic error. And there's actually a really nice demonstration in the paper where we show that as you change your adiabatic curve so that it fully traverses from H0 to H1, the terms you see here in theorem 1 smoothly transition to this second term in theorem 2. And this was our first hint that this is a coherence effect that's somehow changing or strengthening. So I'm going to give a heuristic, not a heuristic, I'm going to give a sketch of the proof for theorem 2. But before I do that, I just want to bang home what this means. So I'm going to extend this sort of sketch that I showed you a few slides back. So I showed you the sort of top half of the sketch where I argued that from traditional first order Trotter bounds, if you're trotterizing adiabatic evolution, you expect to need quadratically more time steps as you increase the total time of your adiabatic evolution. What this new result shows is that you actually can you can actually keep your time step fixed. So in other words, you can increase the number of your time steps proportionally with the total time t. So the bottom half is showing you sort of an adiabatic evolution, and I've made the curve go from 0 to 1 to make it clear that this only holds if you fully transition from H1 to H2. In this case, theorem 2 holds, and what it shows is that because your overall scaling error bound is bounded by 1 over t squared, as long as your delta t is below a certain fixed value, you no longer need to change your delta t to remain below the same error bound. So you can increase the number of time steps and keep your delta t fixed. And so you overall have linear growth in the number of time steps. So this is from a resource theoretic perspective, this is a quadratic improvement in the number of gates you need from trotterization. Okay, so what's happening here? The way that the proof goes is we actually look at the discretized evolution from first order trotterization from beginning to end, and we apply first order time dependent perturbation theory. And what you realize when you do that is you actually get very little Trotter error, formally 0 at the very beginning and at the very end. And that's because in the very beginning, your control curve is near 0, which means you're trotterizing basically just H1. There's no H2 character. So there's no Trotter error. Similarly, at the very end, you're only trotterizing H2. There's very little H1 character, so there's very little Trotter error. And if you formulate this Trotter error in terms of instantaneous eigenstate coupling, you'll see that it turns on harmonically slowly given an infinitely differentiable control curve, and then turns off. So it's like a coupling that's a harmonic perturbation within first order time-dependent perturbation theory. Whenever you have a harmonic perturbation in time-dependent perturbation theory, you basically get what optical physicists call, the Rabi Lorentz curve. So your perturbation, as it becomes longer and longer with respect to the local timescale of the dynamics, its effect decays as 1 over the total time squared. That's the sort of the famous Lorentzian tail scaling. And this is the reason that the probability of excitation, which is basically the infidelity, the probability of excitation out of the ground state gets this 1 over t squared scaling instead of being a t in the numerator. The proof technique is also very interesting because you can look at the upper bound of the error initially, like just as you start the adiabatic curve that you've trotterized. And it reveals a far looser bound there. It's an upper bound, not a lower bound, but we find it numerically that it's frequently saturated. And since it's looser, if it's saturated, this suggests self-healing occurs, what we call self-healing, which is to say that Trotter error or infidelity accumulates with respect to the instantaneous eigenstate and then somehow deaccumulates or self-heals. In particular, we find that the upper bound is order delta t squared, capital T squared. And you can actually see this. This is the same 2-level example where I'm showing you the infidelity, but now on the x-axis, I have the control curve. So it's going from 0 to 1. So in the very beginning, you have very little leakage. And then as you go to the right, your infidelity increases and then somehow goes back to the cumulative infidelity you expect from theorem 2. The different shades of blue curves correspond to different time steps, different delta t. So basically, the higher and darker the color is, the larger your delta t. So you get more intermediate leakage for larger time steps, as expected, because of the delta t squared over t squared scale. So, this is I chose this example because it's a 2-level example. It's easiest to sort of picture perhaps, but also the self-healing curves look damn nice, right? They're like symmetric, but as a result, that looks, might look constructed or artificial or something. So obviously we did numerics on more complex systems. We looked at the ground state preparation for, TFIM. We looked at chemical systems. We looked at Heisenberg. So here you have basically the same scaling. Frequently, the scaling actually outperforms the new bound. The thing I want to focus a little bit more time on is the self-healing. So here is TFIM n equals 4. And you can actually show that, so on the top left graph, this is the eigenspectrum, instantaneous eigenspectrum. So you're trying to stay in level B at all times. But you obviously leak into other ones as you go along this evolution. And in panels B to G, I'm showing the corresponding fidelity in that instantaneous eigenstate. And you can see that there's like pairwise self-healing amongst almost all of the instantaneous eigenstates that you leak into, which is kind of remarkable to see. And there are more examples in the paper if you're interested. We've tried to talk to various people, so we found almost no evidence in the literature or any reports in the literature about this activity. There is some small report for continuous time about some people observing this, but we have spoken to some groups who have seen this and didn't know what to do with it, and so never published. Okay, so the last 5 to 10 minutes, I'm going to talk about the application of an interesting sort of implication or application of this result for QAOA, or the quantum alternating operator ansatz, or some people call it the quantum approximate optimization algorithm. And any questions before I do that? Okay, so
I actually have one.
Yeah.
So there's another very simple problem that I don't think your results directly apply, and I'm wondering whether you could comment on that. So are you familiar with the Landau-Zener problem?
Yep.
So in Landau-Zener problem, it's an infinite time evolution, but you always have diabatic error because you're passing the point of minimum energy gap with a finite speed, even though it's infinite time, because the Hamiltonian will have an infinite norm at positive and negative infinity. So how would what you've done relate to problems like that? Because the diabatic part will never go to zero, even in infinite time.
Yeah, so the Landau-Zener has a lot of very interesting constraints on it. But what I will say is I believe you can actually explain, if you look at these fidelity plots, you see they have a lot of oscillations, like oscillations on top of their overall envelope. And you can actually relate that, the frequency of those oscillations, to the gap between the ground state and that eigenstate. And so what you're seeing is there's a faster timescale process happening here of diabatic evolution that's kind of like a Rabi oscillation, wherein, and this again harkens back to what I said before, where the overall harmonic perturbation is a far longer timescale process than the dominant Short's timescale process, which is basically you can see by this oscillation. And I think you can actually describe the rate of population transfer that this oscillation has going to Landau-Zener in certain approximations. It's a little bit tough because Landau-Zener has like you need like a perturbatively small coupling that scales exponentially with something, I forget what. It's pretty hard to set up, and it's definitely not satisfied in any of the problems I've looked at. But that is what I would point to. Okay, so sorry if you can hear my dog barking in the back. I will talk about QAOA. Okay, so in the original sort of proposition for QAOA, Farhi et al. Kind of postulated that one reason QA is interesting is that it can be thought of as a vanishing time step digitization of adiabatic annealing in the infinite layer limit. And so you can use it to, to do universal things. QAOA, I guess I should motivate, is a sort of classical optimization quantum feedback loop process, wherein you have a sequence of here L gates that alternate between a problem and a driver Hamiltonian. And so you're trying to optimize gamma and beta, the angles in front of in front of HP and HG, such that you produce well, more such that you minimize some cost function, which sometimes is strengthened to such that you prepare some final state. And as gamma and delta vanish and the number L increases, there's this nice limit where QAOA corresponds to an infinitesimal trotterization of an adiabatic process. But in practice, you can often find that QAOA, as you increase the number of layers, has a global minimum that corresponds to a family of curves that do not have vanishing gamma and delta. And so, and in fact, gamma and delta have approach an average, generate a well-defined average that is not vanishing. And so it's tempting to also think to kind of broaden that first bullet point's perspective and say that you can think of it as a finite, perhaps QAOA can be thought of as a finite time step trotterization for annealing for large L. But up until theorem 2, you can't really formalize that because of the naive heuristic that even though annealing fidelity improves with T, standard Trotter error should actually increase with L or T. So our new understanding of digitized adiabatic evolution allows us to kind of establish that QAOA can, in certain regimes, be viewed as a digitization of optimal annealing schedules. So the way we kind of show this is we find optimal QAOA angles for max cut for 3 regular icing problem. Here's shown for 8 qubits. And we plot on the left here, the blue curves, the optimal QAOA angles that we found, where as you get darker curves, that corresponds to more angles, which here are actually parameterized by P. So as P grows, you get darker curves. And we're sort of linearly interpolating them in between each other so that you see that it approaches a sort of universal curve. But notice that so SM here is the ratio of gamma M of the gammas to the sum of the gamma and betas. And you can find that these gammas and betas do not approach 0, so they don't become infinitesimal time steps. Okay, so you take those QAOA angles and you use them to seed an optimal control feedback optimization for finding the optimal anneal curve. So that's kind of shown on the bottom right here. So those yellow dots, somewhat counterintuitively, correspond to the blue, to the discretized blue points. And we use that to initially seed our search algorithm, which then tries to find the nearest optimal anneal curve, which is then shown in blue. And then we plot all those blue curves in orange on the top right. And so they're superimposed, interpolated with each other, just like the blue ones were. Now, keep in mind that again, the time step has it's basically a constant average value. So the darker curves actually have longer total time. We've just stretched them all to look like they're the same length of time so we can compare their overall structure. But the total time as you increase P or as you increase capital T increases, obviously. Okay, so we did that. So we have sort of this correspondence between optimal QAOA angles and sort of anneal curves. And then what we do is we take these anneal curves and we digitize them into a fixed time step trotterization. And sure enough, what you can find is that they approach the originally found optimal QAOA angles as the number of those angles goes to infinity. And you can sort of see that in the bottom right in terms of infidelity of the infidelity of those Trotterized angles, decreases as p goes to infinity. And so this is not a proof of anything. It's just a demonstration of this correspondence, perhaps. But you can use theorem 2 to prove that this must hold in certain regimes. So I'd just like to summarize that, I should mention, this corresponds.
Lucas, I think you're muted. Oh.
Speaker mute themselves.
Looks like he's also frozen, so.
I think it's his internet. It's gone out.
Yeah.
Hey, I sent him a message. Hopefully he'll get it and come back.
All right. Thanks, Mohan.
Yeah.
Hello?
Hey, Lucas.
I take it I fell off a while ago.
Yeah. I think you just went back to talk about the QAOA slide, and then we lost you.
Wow, I'm so sorry about that. I went and finished the whole talk, just so you know, and then for some reason the slides changed, so I didn't notice I was frozen, or I guess whatever. What do you want me to do?
You're welcome to finish your statement, and then I think you're on the last slide anyways, right? So you're more than welcome to finish out.
Okay, I'll try to. There was actually 3 more slides, so I'll just quickly make that one slide on the fly, and then finish up. Okay. So you lost me at this slide, right?
No, so you had gone, you were just showing the QAOA example. Go forward. Yes, right here. So you were here, and then you went to the next slide, and then you came back.
Oh, really? Okay. So I okay, that was, I thought I fell off a lot earlier, so that's great.
Oh,
I
no.
was yeah, I just went back for a moment to say that this correspondence is frequently used to seed higher P initial guesses with lower P guesses, because linear interpolation of the lower P is frequently a very good guess for the higher P. So this is another sort of evidence for this correspondence. Or again, I remind you, P is the number of is L, or the number of layers. So I just wanted to summarize by, hopefully you're still there, with again bringing this this graph. So before this talk, perhaps you would have thought that Trotterizing adiabatic evolution is the same as Trotterizing diabatic evolution or time-independent evolution, wherein if you increase the total time, you need to quadratically increase the number of your time steps and also to scale your time steps smaller proportionally. But hopefully you come away with at least the at least the knowledge that someone thinks that you can actually get away with keeping the time steps fixed and linearly increasing the number of time steps. And thank you very much for bearing with me.
Thank you for the nice talk. So I actually have a couple questions, but I first open it up to the floor here. Does anybody have any questions for Lucas? Okay, then I'll go first here. So you showed this example of the QAOA problem, and you said that that the annealing schedules that they are actually related to the QAOA parameters that you choose. Have you looked at this specifically for cases where you do have well-known analytical solutions, for example, Grover search, where you have a well-known geodesic for the adiabatic evolution, and then also there's analytically derived angles for the QAOA evolution? I mean, those to me that look very different. So actually, I'm kind of curious to know your thoughts on that, and sort of how do those actually connect to each other based off of your findings?
Yeah, so we didn't look at Grover search. We looked at TFIM for just nearest neighbor connected, which has a recursive analytic solution for a family of global solutions of the angles. And actually, it's been noticed before, I believe, in 2019 by some members in NASA, where they showed this sort of correspondence between the discrete QAOA curves and how they showed that they approach a universal family in sort of the same overlapping sense that I showed. I don't know about analytic and annealing solutions. We did that part numerically. I would say that a lot of systems have, an infinity of globally optimal solutions. Some of them even continuously joined to each other with respect to the angles. So it's a very difficult problem to look at numerically. But maybe I should ask you which examples are you thinking about that you don't see this correspondence at all?
Well, I mean, I guess the only one that I could think of, just sort of the top of my head, it doesn't mean it's the only one, but is Grover search, where you have this the analytic path for Grover for the adiabatic Grover looks like a hyperbolic tangent, and you look at the angles that you get from Grover for an optimal Grover search. Right, so if you use you decide on the number of layers you need as an optimal number of or it corresponds to the optimal Grover, and these are fluctuations between this some factor proportional to pi, and then pi being the phase for the problem evolution. And so you have this very much of a bang evolution. And it looks very distinct from this sort of hyperbolic tangent path, that annealing schedule that you see for Grover search, where it slows down during the as you approach the minimum energy gap between the ground state and first excited state, but on the edges it speeds up. So yeah, I guess I'm trying to relate these. I'm trying to see how these results kind of can relate back to yours. I'm not saying that they don't. It's just more of I've wondered about this previously, and wondered if you had any insight on how to actually map this particular problem to it.
The relationship between bang protocols and annealing, has there's some literature on that, some of which I've been involved in. But there's this recent result, I think in PRL with Gorshkov group showed that in the limit that as your timer, your number of bangs goes to grows, the optimal solution must always begin and end with a bang. But in the middle, you can have an annealing region. I never thought about that in terms of Grover or what that means for Grover. But it's what they showed is that in the very beginning and end, even though you have to have a bang, the region becomes infinitesimally small as L or P goes to infinity. So there are some. Again, I don't know how to comment on the Grover algorithm, but you do expect generically for there to be a requirement of bangs, and we kind of obviate that in the Trotterization because you're always technically doing bangs. So I don't know. I don't know of any formal help to any formal statement to add to that. But it is, yeah. The only other thing I would say is that there's a sort of disagreement in the community about, technically, or for a lot of systems, the number of globally optimal solutions proliferates exponentially. And so the continuous one may just be one that we focused a lot on that is not necessarily representative of the global family. I think that's kind of Fari's defense.
Okay, all right, thanks. Any other quick last minute questions for Lucas? All right, well, thank you again for the nice talk. Appreciate it.
Thank you very much.
Thanks, Lucas.
Yeah, thanks. Nice talk.